Hello students. In the previous video, I told you about NSRs, nucleophilic substitution reactions, and I told you about 19 nucleophilic substitution reactions. And in two pairs of reaction, there was comparison. This reaction is faster than this, or that reaction is faster than this, and there was a reason behind it. Similarly, there were some important reactions like why does the attack take place through carbon, not nitrogen, like in the formation of cyanides, and why the attack take place through nitrogen but not oxygen in case of formation of nitro compounds or nitrites. Anyways, we completed all that. Now, in today's video, we'll talk about mechanism of NSRs. There are two types of mechanisms which nucleophilic substitution reactions can follow. These are SN2 and SN1 mechanism. SN2 and SN1 mechanism. S means substitution, N for nucleophilic, 1 or 2 means what? 2 means bimolecular, 1 means monomolecular. Now, what is the meaning of bimolecular or monomolecular? Bimolecular means two reacting particles are involved in slowest step of the reaction. See, if we consider a race, let us say there are 10 participants in that race. The slowest run, when will the race finish? How much time will it take to finish the race? That will depend on slowest runner in that race. Similarly, a reaction takes place in maybe one step or more than one step, which is called mechanism of the reaction. In the slowest step of the reaction, slowest step is called RDS, rate determining step. In the slowest step, that is in the RDS, if two reacting particles are involved, then it is called a bimolecular reaction. And at the same time, we can also call it a second order reaction. These are the terms which will be used in chemical kinetics later on. Similarly, here 1 stands for monomolecular. It means only one reacting particle is involved in the RDS in the slowest step of the reaction, and therefore monomolecular will also be called a first order reaction. First of all, we take up SN2 mechanism, substitution, nucleophilic, bimolecular. In this mechanism, reaction takes place in one step. Since if there is only one participant in the race, he is the slowest, he is the fastest, isn't it? So since only one step is involved in this reaction, it means that step can be called RDS, can be called rate determining step. In this slowest step of the reaction, in this single step reaction, two reacting particles are involved. Therefore, this is called a bimolecular reaction. Look here. Let us say this is alkyl halide. This is carbon atom, alpha carbon. This blue ball represents halogen. Halogen is more electronegative than carbon. Therefore, this bond is polar. Halogen, delta negative. Alpha carbon carries partial positive charge. These three may be hydrogen atoms or maybe alkyl chains. Now, let us say this is the nucleophile, green ball. Nucleophile will attack alpha carbon atom from the backside. So how many reacting particles are involved? One is nucleophile, the other is alkyl halide. Two reacting particles are involved in this reaction, and this is the only step, single step in the reaction. Therefore, this is a bimolecular reaction. So when nucleophile attacks alpha carbon atom from the backside, backside means the side opposite to the side where halogen is attached, backside. When it attacks from the backside, this nucleophile will give its lone pair of electrons. That lone pair will be used to form a bond with this carbon. When this bond forms, at the same time, this bond between carbon and halogen will break, and halogen will leave as halide ion. This goes away. These three bonds will be inverted, means they will come this side. I'll show you with the help of another model. These three bonds will come this side, and this nucleophile will form a bond on this side. Now see how the situation will be. It will be like this. C. Oh, wait a minute. So I was telling you that this halogen leaves as halide ion. This goes away. Nucleophile forms a bond from the backside, and these three bonds will shift that side. It means these three bonds will be inverted like umbrella in a storm. If there's storm and you are holding umbrella, umbrella will be inverted. So see what will happen. These three bonds will be inverted like this. I hope it's clear. And nucleophile will form a bond on this side. This is called inversion of configuration and also called Walden inversion. So how do we represent this? Nucleophile attacks alpha carbon atom from the backside. So called two simultaneous processes will take place. Bond between nucleophile and carbon, alpha carbon, will start forming. At the same time, bond between alpha carbon and halogen will start breaking. And these three bonds will gradually, they are in this side, they will gradually start straightening up. And after that, after some time, this bond will completely form. This bond will completely break. Ultimately, what happens is when this bond is completely formed, it becomes like this. These three bonds are completely inverted on the other side, and halogen is knocked out as halide ion. This is called WALDEN, Walden inversion. Walden inversion, or we call it inversion of configuration, takes place. So I'll repeat. Nucleophile attacks alpha carbon atom from the backside. Bond between nucleophile and alpha carbon starts forming. At the same time, bond between alpha carbon and halogen starts breaking. Ultimately, this bond is completely formed. This bond is completely broken, and halogen is knocked out as halide ion. These three bonds, they are inverted, and therefore this is called inversion of configuration. Particularly, we call it Walden inversion. Configuration means arrangement of atoms or groups of atoms in 3D, in space. That is called inversion of configuration. Now, since two reacting particles are involved in this reaction, this is the only single step reaction. Therefore, this is called a bimolecular reaction. Now, this intermediate is called transition state. This is called transition state. This transition state is momentarily formed. This cannot be taken out from the reaction flask. And this is highly unstable. Why this is unstable? Because in this transition state, carbon appears to be forming 5 bonds. Therefore, energy is very high. Stability is very low. Therefore, this cannot be taken out from the reaction flask. Now, coming to the reactivity by this mechanism. If this alpha carbon atom is attached to hydrogen atoms, hydrogen will occupy less space compared to any alkyl chain. If there is one alkyl chain, 2 hydrogen atoms, it is primary alkyl halide. If it is attached to 2 alkyl chains and 1 hydrogen, this is secondary alkyl halide. If it is attached to 3 alkyl groups, then this is called tertiary alkyl halide. So this is primary. Now this is secondary. Now this is tertiary alkyl halide. Since alkyl groups will occupy more space, therefore, approach of nucleophile to this alpha carbon atom will become difficult. Why does it become difficult? Due to hindrance, due to steric hindrance. I hope you remember, you studied about steric hindrance in 11th standard. So more the number of alkyl groups attached to alpha carbon atom, more is the steric hindrance, and therefore difficult is the approach of nucleophile to alpha carbon atom, and therefore lower is the reactivity of alkyl halide by SN2 mechanism. It means I can say reactivity order of alkyl halides by SN2 mechanism is primary, faster than secondary, faster than tertiary. So tertiary alkyl halide will be least reactive by this mechanism. Now the second mechanism, second mechanism is SN1 mechanism, substitution nucleophilic monomolecular. In this case, in this mechanism, reaction takes place in two steps. In the first step, look here. In the first step, bond between carbon and halogen will break heterolytically. Heterolytically means both the electrons of bond will be taken away by halogen, which is more electronegative. After this bond breaks, this will lead to the formation of positively charged carbonium ion. It is something like this. This bond between carbon and halogen will break heterolytically. Along with pair of electrons of the bond, this goes away as halide ion. This carbon will carry positive charge, and this is carbonium ion. Remember, carbonium ion is triangular planar. It means this and all these three, they all lie in the same plane. It is a flat particle like this. Looks like this. All the angles are 120 degree. Now, in the second step, this carbonium ion, which is flat, this will be attacked by the nucleophile in second step. Now, this attack of nucleophile can take place from either side. If attack of nucleophile takes place from either side, then these three bonds which are flat will come back to their original position. If attack of nucleophile takes place from this side, then these three bonds will be inverted. Since there is 50-50% chance of attack of nucleophile from either side, this will lead to the formation of a mixture which is called racemic mixture. Remember, chemically product is same, but arrangement of bonds in 3D is different. 50% product molecules will have the same configuration as the configuration of the reactant. We call it retention of configuration. Whereas 50% product molecules will have an inverted configuration. This mixture of products is called racemic mixture, and the process of formation of a racemic mixture is called racemization. How will this mixture look like? Let me show you. See, if nucleophile attacks from this side, these bonds are inverted and nucleophile forms a bond this side. Second case, if nucleophile forms a bond from this side, then green bond will be this side, and these three bonds will be on their normal side, initial, that is retention of configuration. This will be the configuration, right? So chemically, it represents the same molecule, same compound, but arrangement in 3 dimensions is different. This is called racemic mixture, and the process of formation is called racemization. Now, let me represent this racemization. In the second step, nucleophile attacks. If nucleophile attacks from this side, we get this product. If nucleophile attacks from this side, we get this product. Chemically, this is same, and we call it racemic mixture. Now, after 2 steps, which step is slow? Because that is going to decide whether this is monomolecular or bimolecular. See, in the first step, bond between carbon and halogen is broken. And for breaking this bond, energy is required. That is why step 1 is a slow step. Step 1 is RDS. Since only one reacting particle is involved in the RDS, this is a monomolecular reaction, that is SN1 mechanism. Now, as I said, energy is required for breaking of this bond. From where does this energy come? Energy comes from solvation of this halide ion. After breaking the bond, halide ion will be released. This halide ion will be solvated. Solvated means that this reaction will be carried out in the presence of a solvent. And the solvent used is generally a polar solvent, like water, alcohol, or acetic acid. This type of polar solvents can be used. Polar solvent will form a cover around halide ion. Formation of a cover of solvent around any solute particle is called solvation. During the solvation, some energy is released, which is called solvation energy. And the same energy is utilized for breaking of the bond, right? So this is the reason reactions by SN1 mechanism take place in the presence of polar solvents, which may be water, maybe an alcohol, or maybe a carboxylic acid. Now, I've told you both the steps. Now coming to reactivity order by this mechanism. In step 1, carbonium ion is formed. You studied about stability of carbonium ions on the basis of hyperconjugation in 11th standard. So according to hyperconjugation, stability of carbonium ions is tertiary more than secondary more than primary. Since tertiary carbonium ion is most stable, it will be easiest to form tertiary carbonium ion, followed by secondary and followed by primary. This is the reason tertiary alkyl halides react fastest by SN1 mechanism. Primary alkyl halides react slowest by SN1 mechanism. And this order of reactivity is opposite to the reactivity order by SN2 mechanism. In SN2, primary reacts fastest, tertiary reacts slowest. Reason in that case was steric hindrance. In case of SN1 mechanism, tertiary reacts fastest, primary reacts slowest. And in this case, reason is stability of carbonium ion on the basis of hyperconjugation. But at the same time, remember, there is no NSR which 100% follows one of the two mechanisms. Means what? There's no nucleophilic substitution reaction in which all the reacting molecules will react by either SN1 or by SN2 mechanism. If we say this reactant, this alkyl halide reacts by SN2 mechanism, it means most of the reacting particles follow SN2 mechanism, but there may be some molecules which will follow SN1 mechanism as well, right? Same is the case with SN1. Now, in SN1 mechanism, I said primary react least, their reactivity is least, but there are two exceptions. There are two primary halides react by SN1 mechanism, but their reactivity is more than expected. What are these two exceptions? Primary allylic halides and primary benzylic halides react by SN1 mechanism because carbonium ions formed by both of them are stabilized through resonance. I'll show you how. I'm taking first exception, primary allylic halide. Primary allylic halide. In step 1, this bond breaks, halogen leaves as halide ion. This will lead to the formation of carbonium ion. This carbonium ion can stabilize itself through resonance. Since this carbonium ion is, although primary, but stabilized through resonance, it means the reactivity of primary allyl halide by SN1 mechanism is fast. It is more than expected. Second exception is primary benzylic halide. This is primary benzylic halide. Step 1. This bond breaks, halogen leaves as halide ion, and this leads to the formation of primary benzylic carbonium ion. But this carbonium ion can stabilize itself through resonance. Now again, since this primary benzylic carbonium ion is stabilized through resonance, it means primary benzylic halides preferably react by SN1 mechanism. Although they are primary, but they follow SN1 mechanism. Now we can conclude like this. We can conclude that primary allylic, primary benzylic halides follow I'll repeat, primary allylic, primary benzylic, and tertiary alkyl halides. They follow SN1 mechanism. Second, primary alkyl halides almost always follow SN2 mechanism. Similarly, primary wait a minute. Okay, I'll repeat. So we can conclude that primary alkyl halides almost always follow SN1 mechanism. Sorry, SN2 mechanism, because there is least steric hindrance. Number 2, tertiary alkyl halides almost always follow SN1 mechanism, because tertiary carbonium ion is stabilized through hyperconjugation. Number 3, primary allylic, primary benzylic, and secondary alkyl halides. They can follow either of these two mechanisms. Either of two mechanisms can be followed by them. Now, in the conclusion, I told you that secondary alkyl halides, they can follow SN1 or SN2 mechanism, both. Now, here I'm taking two special examples which will be helpful in your competitive exams. If a secondary alkyl halide undergoes NSR by SN1 mechanism, then in some cases, 1-to shift means shift from carbon number 1 to carbon number 2. 1-to shift of hydride ion or methyl ion can take place, which will lead to the formation of a more stable intermediate carbonium ion, and then more stable carbonium ion will be attacked by nucleophile in the second step to give a more stable product. This will be clear only with the help of example. I'm taking the example of secondary alkyl halide, which follows SN1 mechanism, and 1,2 shift of hydride or methyl can take place. I'm taking first example. This is 2-bromo 3-methyl butane. If this compound undergoes NSR by SN1 mechanism with aqueous NaOH, SN1 mechanism reaction with aqueous NaOH. In step 1, halogen will leave as halide ion, and this will lead to the formation of carbonium ion. Now, this carbonium ion will undergo 1,2 hydride shift. H minus from this carbon atom will shift to this. Now, why will this shifting take place? This is a secondary carbonium ion. But if this H minus goes to this carbon atom, then positive charge will come on this carbon atom and lead to the formation of a more stable tertiary carbonium ion. This is 1,2 hydride shift. And this will lead to the formation of a more stable tertiary carbonium ion. Now, in the second step, this will be attacked by hydroxide ion of aqueous NaOH and give the final product. So product formed is 2-methyl-2-butanol. So if you do not think about hydride shift, then you'll probably attach a nucleophile to this positively charged carbon atom, and the product probably will think that the product is 3-methyl-2-butanol. No, product is not 3-methyl-2-butanol. Product is 2-methyl-2-butanol. But remember, at the same time, this much detail is not required for your CBSE exam. In case the same thing is asked in your board exam, CBSE exam, then do not think of this hydride shift. Attach hydroxide ion to this carbon atom. Product will be 3-methyl-2-butanol according to CBSE. According to CBSE. But if you are attempting any entrance exam, then think of hydride shift. Secondary carbonium ion will change into a more stable tertiary carbonium ion by hydride shift, and that will be followed by attack of hydroxide ion and give tertiary alcohol as the final product. I'm taking one more example. This is 3-bromo 2,2-dimethyl butane. 3-bromo 2,2-dimethyl butane. In step 1, again, bromine will leave as bromide ion. This will lead to the formation of a secondary carbonium ion. Now, in this case, there will be methyl shift. Methyl along with electron pair will shift. This is called CH3 shift. And this will lead to the formation of, you can see, secondary carbonium ion changes into a more stable tertiary carbonium ion. And this will further be attacked by hydroxide ion in step 2 of the mechanism, that is nucleophile, and will lead to the formation of final product. And you can see final product obtained is 2,3-dimethyl-2-butanol. Again, in case you are facing the same reaction in board exam, then do not think of this shift. In second step, attach nucleophile to this carbon atom, and the product form will be 3,3-dimethyl-2-butanol. Right? So this is the difference between your board exam, board preparation, and mains preparation. Right?